Hello there. Today, we'll be walking you through our adapted 3D model of the veterinary hospital in the campus. My name is Daniella, and as the structure is the skeleton of every building, I will start by explaining that. The structural design is a combination of steel, timber, and concrete elements, each one carefully chosen for its functionality, strength, and sustainability. Let's start with the steel structure. Here we're using IPE 450 beams, ensuring low distribution and open spaces, having big spans of almost 8 meters. And we have HEB 160 columns, carrying the vertical loads to the foundations. To further stabilize the structure, especially against lateral forces like the wind, we have incorporated circular hollow bracings of 12.5 centimeters of diameter and 5 centimeters of width, having 2 frames placed in each direction, north-south and east-west, plus additional bracing in the stair framework. We also have the elevator box as an extra structural element. Moving on to the slabs, for the upper levels we're using 39 centimeters thick glue-laminated timber slabs, chosen not only for its sustainability but also for its high performance properties such as durability, flexibility in design, and high strength to weight ratio. These timber slabs are connected directly to the steel beams, creating a cohesive system. The 30 centimeters thick reinforced concrete slab in contact with the ground provides a solid base and moisture protection from the soil. For the foundation system, first we have 30 centimeters thick retaining walls designed to hold back soil and prevent lateral earth pressure from compromising the building structure. They are supported by footings of 2 sizes. One is 60 centimeters wide, having 30 centimeters in each side of the wall, and the other one is 30 centimeters wide, having it just in the interior retaining wall. For the inner footings, we have 3 sizes, the largest one being 220 x 220 x 90 centimeters, and the other ones sized 180 x 180 x 50 centimeters height and 60 centimeters height. These footings are distributed based on the placement of the columns, load conditions, and soil characteristics. To ensure proper distribution of loads and to align the footings, we have included centering beams of 30 x 60 centimeters. Now, let's take a closer look at the connections. The circular bracings are welded to the HEB column for a strong permanent connection. They are attached to the IPE beam by using metallic plates and bolts. The beams sit on the columns, and the timber slabs are connected using steel plates, screws, and bolted joints, securing the timber to the steel structure. In conclusion, the design optimally combines steel, timber, and concrete for durability, sustainability, and functionality, while optimizing performance and minimizing cost and environmental impact.
In our building, we have a pressurized water distribution system. It starts at the main line connected to a pressure tank and 2 accumulator tanks on the first floor. From there, it is distributed through PVC pipes through all fixtures. On the ground floor, the water flows through 2 shafts and then through a false ceiling with 2% slope to ensure efficient flow. Hot water is provided through a centralized hot water system, distributing heated water from 2 boilers via insulated pipes to all fixtures. The hot water follows the same path as the cold, traveling vertically to 2 shafts and horizontally to a false ceiling to reach both floors. The drainage system is a combined drainage system for black and gray water routed through a suelo técnico on both floors. It includes ventilation pipes throughout the system, and drainage is managed through a suelo técnico for easy access before being directed to an outside pipe. A modification was made to the drainage system to handle infected water from specific rooms. This water is collected via gasket and treated in a tank located within the building, as you can see in the model. This ensures the safe management and disposal of potentially dangerous wastewaters to prevent contamination. Rainwater is handled by a rainwater drainage system which combines with the foundation drainage near the retaining wall, ensures proper water management and preventing water from pooling near the building. The foundation is protected by a perimeter drainage system. This system prevents the water accumulation around the system and helps maintain the building's structural integrity. The final model that you see is a result of some adjustments that were made due to conflicts with the structural beams that are further explained in the memoria.
For installations, each element and each pipe has been strategically placed for simplicity and efficiency. The layout minimizes unnecessary pipes, ensuring a faster installation process and reducing material use, By optimizing space, we've also preserved more area and more control within the drop ceiling. For heating and cooling, each room is equipped with a DDF heat beam by trucks, receiving cold and hot water along with the return pipes. Fresh air is delivered directly to each beam through the 123mm air pipe from the air handling unit. Ventilation out is handled by Lunus Silvento fans, each capable of handling up to 90 cubic per hour of air. For bathrooms, same system, but separate pipes are placed to ensure the optimal exhaust and air quality. The design of the pipeworks ensures minimal overlap in both plan and elevation views, reducing the need for excessive material and minimizing potential failure points due to unnecessary connections. For the electrical system, the main centers are located inside of the building for safety and access. The circuits are divided to cover around 150 meters squared each, ensuring a better control and safety throughout the building. This integrated approach, by carefully placing elements, minimizing the material use, and moving forward to a more lean construction, guarantees a safe, affordable, and well-organized solution for ventilation, heating and cooling, and electricity.
Let's start with the interior envelopes. First, we're going to talk about the floors. The first typology is a technical floor elevated 200 millimeters so that the sewage pipes of the installations can go through and have easy access for maintenance. It is made of 600 by 600 millimeter tiles, topped with a 3 millimeter rubber layer to enhance cleaning. This seamless flooring is used in the treatment areas, allowing for quick sanitation, which is essential for maintaining a hygienic environment. Our second flooring option consists of a 3 millimeter rubber layer over 30 millimeters of mortar, coupled with 20 millimeters of acoustic insulation. This flooring is installed in the first floor to reduce noise transmission, creating a quieter space for the most private rooms. To continue with the walls, we have 4 typologies. The first typology is a double gypsum board system consisting of 2 layers of 12.5 millimeter gypsum board on either side of rock wool insulation that uses a timber frame as a secondary structure. This gypsum board is supported by an aluminum frame, and the configuration is primarily used in private areas like examination or surgical rooms. Our second typology features timber louvers that are attached with a steel channel connector to continue with the exterior envelope. This design is commonly found in public areas like reception or the waiting areas. For critical areas requiring fire safety, we utilize fire-rated gypsum board system. This typology is strategically placed around escape routes and emergency exits to protect against fire hazards. Finally, our glass wall typology is only placed in the specific rooms that need a visible connection between each other. Finally, let's discuss our ceiling designs. In public areas such as reception and waiting rooms, we feature a wooden slat ceiling. The ceiling hangs 550 millimeters from the slab, allowing room for installations underneath, while integrated linear LED lighting into the wooden slats, providing a warm ambience and illuminating the space effectively. In private areas, such as consultation or operational spaces, we use a gypsum panel ceiling. Also suspended 550 millimeters from the slab, the ceiling features a 20 millimeter gypsum panel, allowing as well easy access to electrical installation and housing specialized lighting features tailored for each room specification.
Let's examine the building system, starting from the interior ground floor and moving outward to the rooftop. After the interior layering, a 30 millimeter mortar screed supports the technical floor. Underneath the screed, there is a 450 millimeters of insulation, providing both thermal and acoustic performance. This entire system sits on a damp-proof membrane to prevent moisture from rising into the building. For the wall system, we have 2 typologies. For private walls, in private areas of the hospital, the wall assembly begins on the interior with 2 layers of gypsum board. They are fastened to an aluminum frame which provides structural support. Behind the gypsum board, there's 120 millimeters of insulation, improving the thermal performance and soundproofing. Next is a waterproof membrane, which protects the structure from moisture. Outside the membrane is a timber substructure that supports the exterior cladding. Finally, the outermost layer consists of timber louvers separated by battens with an air cap of natural ventilation. For public areas, the wall system is similar, but with timber louvers applied inside and out. Some sections of the building feature glass windows for increased transparency. This window starts with double glazed system, 2 layers of 6 millimeters thick glass separated by a 12 millimeter air cap for insulation. The windows are framed by a durable 2.5 millimeters thick aluminum frame that provides structural integrity and thermal performance. The last typology we're going to show, the walkable rooftop. From the interior The roof begins with a structural concrete slab of 450 millimeters thick. Above that, we have a 30 millimeters thick mortar screed with a 5% slope for drainage. This is followed by 150 millimeters rock wool insulation, helping to manage the building's thermal load. A waterproof membrane is applied next. And on top of that, there is a 550 millimeters ventilated gap. For the final layer is 20 millimeters thick concrete pavement, which provides a slab walking surface while allowing for proper drainage and ventilation. To finalize with the exterior envelope, I will turn on the external timber louver layer to visualize the full model. As seen in this volumetric section, all components of the building envelope integrate smoothly. Starting from the ground slab, the architectural layers are carefully arranged, with space for installations beneath the technical flooring. The wall system is designed to accommodate piping and utilities efficiently. The structural elements connect smoothly with the wall system and false ceiling, where additional installations are placed, ensuring no overlap between systems. Finally, the ceiling leads up to the walkable rooftop, which includes an air gap for rainwater drainage and natural ventilation. Each layer of the building envelope is carefully designed to enhance energy efficiency, comfort, and durability, creating a high-performance environment essential for a veterinary hospital.